Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
What is Philip Emeagwali famous for? In 1989 and thereafter, I was in the news headlines because I was the first full-time, massively parallel processing supercomputer scientist to figure out how to solve the grand challenge problems arising in mathematical physics and figure out how to solve them at the fastest speeds in supercomputing. That contribution to the development of the computer was the reason I was in the news headlines and the subject of school reports since 1989. I was the first person to deliver a complete set of lectures on the massively parallel supercomputer that was the precursor to all modern supercomputers. Back in 1982, mathematics research seminar that I gave in Washington, D.C., I was asked, "Why do you lecture without notes?" I explained that I lectured without notes because I invented the 9 Philip Emeagwali equations that were not in existing textbooks, and that I invented those equations without looking at notes and without reading them from textbooks. That is, I speak calculus with the fluency I speak my ancestral Igbo language that I speak without English to Igbo dictionary. To this day, my schoolmates at age 15 and back in mid-1970 at Christ King College, Onitsha, Nigeria, still call me by my nickname, Calculus. Before my discovery of practical parallel processing that occurred on the 4th of July 1989, I had a tacit or theorized knowledge of how to parallel process real-world problems and how to solve them across a new internet, that is a new global network of 64 binary thousand processors. After my discovery of practical parallel processing, my knowledge of the new supercomputer became explicit, not tacit. After the 4th of July 1989, my discovered practical parallel processing was no longer a theory or an idea that is not positively true. I was able to write that knowledge down in my 1057-page supercomputer report and to win in 1989 the top award in the field of supercomputing. That award recognized my contributions to quote-unquote practical parallel processing. I did not study parallel processing. I started the field of practical parallel processing. My discovery of practical parallel processing shed new light on the ways the new supercomputer scientists can translate old physics into new calculus, discretize that new calculus into never-before-seen extreme-scale algebra, and then code the solution of that new algebra into new arithmetic or into an equivalent set of floating-point arithmetical operations that demands a new supercomputer that occupies the space of a soccer field. My discovery of practical parallel processing made the news headlines because it applied to all initial boundary value problems. The partial differential equation that governs an initial boundary value problem arises in numerous contexts and across mathematics, science and engineering, and medicine, and particularly in fields such as non-relativistic quantum mechanics, general relativity, elasticity, electromagnetism, and hydrodynamics. The parallel processed solution to a grand challenge problem is extremely knowledge intensive, and for that reason, it is a problem that is best tackled by a large team of seasoned research computational scientists. For me, Philip Emeagwali, solving that grand challenge problem alone was like diving to the deepest known point in the Earth's oceans, that is 36,070 feet, or almost 7 miles below sea level, that is called the Mariana Trench. That's why it took me more than a decade to figure out how to solve grand challenge problems and how to compute their answers across an ensemble of millions of processors.
Insightful and brilliant lecture.